Hi everyone, welcome to lesson 3 of the motor effect. I know it says motor effect 2, please ignore that. This is in fact motor effect 3. Please, if you could title and date, that would be fabulous, and then we shall move on. So, last lesson we looked at how a motor works. Previous to that we had looked at Fleming's left-hand rule, and the idea that if you put a current carrying wire, there's my current carrying wire, in a magnetic field, here's my magnetic field, then it will be repelled. We use Fleming's left-hand rule, if you remember, to tell you which way everything should go. So your thumb, your first finger, your second finger. Your thumb representing the force or the way that the wire will move. Your first finger representing the field. So it was movement, the field, and your second finger representing the current. So I'd like you to very quickly have a little look, this is north, this is south, at that very sketched diagram that I've done, and just check that you can use Fleming's left-hand rule to tell me which way that wire is going to move. So just a reminder, gun, pow, in terms of setting up your fingers. So gun, nice right angle between your thumb and your first finger, pow, stick your middle finger out, so again you've got another nice right angle. So please pop that in, use it on that diagram and tell me which way it will move. Okay, I've done it. I'm hoping you've all had a chance. I'm estimating that it would move up. That's it. Hopefully that's nice and easy. So today, what are we looking at? Why a wire in a magnetic field feels a force. When a current carrying wire is placed in a magnetic field, the fields combine. Where the two fields face the same direction, a strong force is created. I will show you the diagram I'm talking about in a moment. Where the two fields face opposite directions, they act against each other, creating a weak force. Overall, a force is created to move the wire out of the magnetic field of the permanent magnet. I'm just going to delete this because it always goes funny. So let's have a little look. Here is a diagram. On the left, you have the magnetic field of a bar magnet, and then in the middle, a magnetic field of a current carrying wire. You can see the wire is going to be placed inside that magnetic field of the bar magnet. On the right is the combined result of their fields. So if you have a look at the top of both of the individual field diagrams, you will see that the fields are going left to right. So they're going in the same direction. So on the combined diagram on that right-hand side, you end up with a much stronger force because they add together. At the bottom of the individual diagrams, you will see one of them is pointed left to right and the other is pointed right to left. That means they are going to act against each other. Excuse me, sorry. And so at the bottom of the diagram where they are combined, you will see there are less field lines and a much weaker force. And so here, can I write on this? Yes, I can. Here they are combined, added together. So you've got a strong force at the top pushing down, and you have a weak force at the bottom where they've been combined, I'm going to say, but subtracted because they're going in opposite directions. Subtracted is probably the word I want. Combined but subtracted. So you've got a much weaker force pushing up here. And so overall, this wire will be pushed downwards because of that strong force on top. Now this is called the catapult effect. And it's the reason, that's a T, sorry. It's the reason that wires are moved out, of why the motor effect actually happens. So if you go back in the video and have a look and you take the notes from why that happens, and then if you could get these diagrams down as well, that would be fabulous. Oh no, now how do I get rid of this? Oh dear, shouldn't have drawn so much. Nearly there, come on. Fabulous, right. There you go, there you go. Oh, here we go. There's the notes you saw before. So here is an equation. We can calculate the force on a wire using the equation F equals Bill. F is the force on the conductor, the force on the wire, and it's normally measured in newtons, just like any other force. B, I'm going to come back to because it's slightly more complicated. I is the current through the conductor, remember from our electricity topic, measured in amps. L is the length of the conductor in the field. Do you remember whenever we've got the loop of wire but only one bit of it is in the magnet, I only ever care about that bit. It's this length, how much of the wire is in the magnetic field. Okay, so let's go back to that B. B is called magnetic flux density. And it was discovered by someone called Nikola Tesla, who's over here, smizing in the corner. I always think he looks like he's auditioning for America's Next Top Model. There's definite pout going on there. Anyway, it is effectively, magnetic flux density, the strength of the magnetic field. The bigger the magnetic flux density, effectively the stronger the magnet. And it is measured in Tesla. You may also recognise the name Tesla because obviously the car Tesla was named after Tesla. You can also get things called Tesla coils. This guy was very clever. As well as being a bit of a pouter and a model, he was also very clever. So well done him. So let's have a go at a practice question. What is the force on a wire of length 5 centimetres carrying a current of 2 amps in a magnetic field of flux density 5 Tesla? So F is Bill, B was 5 Tesla, I, 2 amps, L, 5 centimetres. Now length should always be in metres, so I've turned it into metres here. You'll see I've put 0.05. Times it all together and you get 0.5 newtons. Let's rearrange it. What is the current through a 10 centimetre wire if it experiences a force of 20 newtons whilst in a magnetic field of 4 Tesla? If you would have a triangle, it would be F on top. So I is F. Sorry, I put that in the wrong place, didn't I? Oh no, mistake. Apologies. Right. I is F divided by B times L. F was 20. B, 4. Nice and easy. L, again, notice it's 10 centimetres, so it's got to be 0.1 metres. Pop it into your calculator. Make sure this bottom section is in brackets, otherwise you'll end up with some funny numbers. You get an answer of 50 amps. Okay, have a little go at these, pause the video, and then I'll go through the answers. Okay, so hoping everyone's had a go at those. Number 1, what is the force? So we're working out F, which is Bill, so 2, because it's for current, 3, length, 0.06, which gives me 0.36, and it's a force that's measured in newtons. I is F over BL, so that is 24 over 2.5 times 0.08, which gives me 120, and it's current, so it's measured in amps. I'm going to underline my answers so they pop out nice and easily. Number 3, working out length, which is F over BI, so that's 30 over 2 times 10, which gives me 1.5 metres. 4, working out F, so that's Bill times them all together, 3 times 7 times 0.02, which gives me 0.42 newtons. 5, current, which is F over BL, so that's 40 over 8 times 0.02. So, where are we? 40 divided by 0.16. Give me 250 amps. And final one, L is F over BI, is 45 over 3 times 15, 3 times 5, which gives me 3 metres. Right, hope that makes sense, everyone. Please let me know if you've got any issues. Thank you.